So just in terms of understanding the audience here, are we all interested, what are the primary topics of interest? Is this exploration from your perspective, robotics, automation? Who's in for solar system exploration, expanding the solar system? Outstanding. Anyone here particularly into robotics, machine intelligence, and other systems? Awesome. And a good bit of overlap as well. I like that. I like that. Well, look, I think we've got about an hour here, so we'll try and make this fun and a little informal, so feel free to stick your hand up and ask any questions as we go along as well. And I'm going to tell a little bit of a story of OffWorld, but also OffWorld in the context of what we're doing as a planet, what we're doing as a civilization, and really, what are we trying to achieve and what are the real goals we should be looking at as we move forward beyond low Earth orbit and geostationary orbit. So why don't we kick off and we'll go from there. So first I'll introduce you to one of our teammates who will kick off the proceedings. And if we have some volume, please.
I come from a new generation of industrial robots. Unlike our ancestors, we are designed to learn. We learn from humans, from our own experience of the real world, and from millions of simulations. Our job description is simple: make human dreams real. Build orbital stations and solar farms in free space. Return to the moon. Mine asteroids. Build cities on Mars. Get comfortable in the inner solar system. One day, tens of thousands of us will be working for you off-world. To get to that day, we have quite an evolutionary path in front of us. First, we must master basic industrial jobs on our home planet. We are now busy learning from experienced human teachers. Together, we are reinventing how to mine, process, manufacture, and build cities on Earth. This is no small feat. This step will keep us busy for several years to come. Technologically, our homeschooling will get us about 80% of the way to orbit and the moon. In the next step, we must evolve and adapt our bodies and our brains to the much harsher orbital and lunar environments. The evolutionary jump from our orbital and lunar surface generations to generations fit to work on asteroids and Mars will be kids' play compared to the first two steps. A few minor tweaks and we will be ready to mine asteroids and get the red planet ready for human arrivals. With thousands of us deployed across the inner solar system, we will need to think seriously about scaling. How do we replicate ourselves locally and decrease our dependence on resupplies from Earth? We will start small and slowly work our way through the parts list. The crowning achievement in our quest for local replication is manufacturing this solar system's first off-world chip. On that day, we will have made history. But let's not get ahead of ourselves. We must get back to reinventing industry on Earth.
So that's just a little momentary introduction to OffWorld and what we're attempting to do over the long arc. We're building a solar system toolkit that can enable us to do any task under any conditions in any location in the solar system. This is a bold and ambitious statement, but actually, when you characterize the technological tasks required to undertake this, when you solve fundamentally for one environment or one task, the engineering delta to progress to the next becomes step-by-step incrementally lower. So by fragmenting or pixelating the hardware, as we call it, we can generate and build millions of robots operating in swarms, speciated by task, by capability, and collaborating and working together to produce significant solutions to existing challenges that we face in multiple industries. And we face a number of significant challenges here on Earth. As a species, we have three fundamental concerns that are facing us. And the concerns are of such an urgency, yet so elusive and intangible, that the contradictions cause us en masse to pay very little attention to them. One of the first undertakings of OffWorld is to ensure that, along with many of our colleagues in the community and elsewhere, that we provide a life insurance policy for our civilization and species against the risk of existential calamities and catastrophes. By ensuring that we have capability both resilient on the planet and off planet, this allows us to ensure that anything untoward, like an asteroid strike or other existential level risks, don't wipe out the human race. This has got to be a fundamental requirement of our species. I'm sure many of us would agree with that if we can find a way to achieve that kind of capability. The second big issue is to maintain sustainable life here on Earth. Earth is in a meadow of the habitable zone around the only star we know how to live on or live around. This habitable zone and the planet that we're on is so delicate and fragile. We don't understand the limits of that fragility because we've never reached them. And as a species and as a mass population, we tend not to react or tend not to act in the face of impending dangers. We only tend to operate by reaction en masse. So the few of us who have the ability to execute particular solutions to mitigate these sorts of risks to life on Earth should work to do so. And for example, this includes taking off as much industrialization from the surface of the Earth as we can over the next 100 or 200 years by removing energy generation, heavy-duty processing and manufacturing, and other heavy polluting industries, by reducing the amount that we have to mine and extract mineral resources on the planet over the next 100 to 200 years, by managing the needs of a potential 10 to 15 billion person population on the surface. We cannot scale to this level of growth, humanity growth, and the level of consumption without significant changes to the methodologies that we extract mineral resources here on Earth and the processing and manufacturing systems that we do use. So just as if we were living in a meadow or a field here on Earth, we wouldn't start operating a processing industrial plant or an oil refinery in our forest. We would move that well away so that we'd maintain that local habitat. Well, Earth is a local habitat and we have to maintain that. So that is one of the key drivers for wanting to get out into the solar system and into space. And of course, as a species, finally, we've always had an open geographic frontier. This is something that we have lost over the last 100 years or so. Our ability to expand our frontiers and our horizons beyond what we can see. And over the last 100 years or so, we have created overlays of new frontiers in different contexts and different dimensions, whether they're technology dimensions, economic dimensions, or otherwise. But the challenge with that is our human instinct is to gather resources, to maintain security for ourselves and our loved ones, and to ensure that we are safe and protected and fed. The challenge with that is that it drives a culture and a paradigm of scarcity. When you're driven en masse by a paradigm of scarcity, the conflicts that emerge, the challenges that emerge for resource acquisition, for land, for territory, exacerbate and continue to grow and grow. And we begin to see some of these drives and some of these challenges here on Earth as resource-based conflicts and territory-based conflicts create additional tension. So opening up the solar system to explore, to reach out, to open up the frontier, to regain our edge as a species, to allow those in the population who wish to look forward and out into the unknown and take those risks. As we journey out to the solar system and into the stars, we need to enable those capabilities and opportunities. And that should be done within the next 100 to 200 years as well. So those are the three main paradigms that we have. And that's underpinned to a great extent by the prospect of settlement in space. But settlement has always been hard. It's often used by force. It's often been driven by those who wish to escape persecution or seek a better existence somewhere else. But there's always been hardships. The transits have been hard, living conditions have been tough, and throughout history, generations have effectively lived in extremely harsh conditions in the pursuit of settlement to new territories. And in space, settlement is just an even harder prospect. We're now without the protective envelope of our Mother Earth environment, often without atmosphere, variable gravities, harsh radiation and debris environments, conditions that would drive the harshest environments here on Earth, make them look like quite livable situations. Our bodies are unfortunately very adaptable to change in this way. So different gravity and atmospheric conditions can force our bodies, both genetically and physiologically, to adapt in ways that we just don't know what the results would be. And of course, there is no ability to perhaps plow the land indigenously. And most of all, I think from an economic and institutional perspective, every time we have undertaken settlement, every time we have undertaken infrastructure build out into different territories, we have always used the lowest common denominator of labor cost. This has been the real challenge, is that for many thousands of years it has either been slave labor or forced labor. As we go exo-atmospherically into the solar system, the astronaut ostensibly is the most expensive form of labor and the most expensive and valuable asset. The human in space is a delicate, fragile system, highly expensive to operate, highly expensive to protect and to nurture. And so we have to see, if we're going to really build out into the future, if we're going to build systems on a production level, we can't just carry on our one-off exploration culture, engineering culture of one or two systems built to operate in this harsh environment with 1,000 people monitoring and operating them either in situ or remotely. So we need tough jobs to be undertaken in space. Before it is safe, before it is effectively practical for people to operate and live with a reasonable risk profile of being able to survive the day, we need to build landing pads for safe landing so that we don't kick up regolith and dust out into the environment. We need to build underground habitats to protect from radiation, have water, materials, propellant, and food ready for use. Have these systems enabled to manufacture, to fabricate, and to produce power. So how do we do this? Well, we can build one-offs as we have done over the last 50 to 60 years. And the challenge is we can't just export current Earth technology, but we need to figure out a way how to reinvent how we build systems, how we manage our industrial systems here on Earth. And currently we've constantly used, especially the last 150 years or so of the Industrial Revolution, the human operator or the blue-collar worker, to a great extent, has been the intelligence element in an automation supply chain of increasing complexity and fidelity. But as we go out into ever more extreme environments, as our automations become ever more involved and precise, the strain on individual human workers and operators, both in normal urban and extreme remote environments, becomes intolerable. So we need to figure out a new way to do things, and that's what OffWorld has been doing. And we are building on a heritage of decades in robotics and automation technology. But this is an old class in the space context. This is a class of exploration vehicle. The exploration spacecraft, or the exploration methodology of spacecraft build, is extremely high quality control, extremely expensive, clean room build environments, a high degree of operator to robotic ratio, and using limited autonomy where available. This is expensive. It drives up the cycle costs and the cycle times. It usually means by the time you want to build a second one, the technology field has moved on, and you can't even procure the parts and the systems that you already built with, so you have to redesign again. So we need a new paradigm. We need to go from the exploratory vehicle architecture to the exploitation spacecraft architecture. Ruggedized, autonomous, collaborating units, working without human intervention in real time. These units need to be low cost. We need to build in the thousands to hundreds of thousands to millions of robots. We should set standards that allow these robots to interact and communicate across a single operating digital platform. They need to operate autonomously, be modular so that we can undertake multiple configurations of any variety and type. And most importantly, both here on Earth, which is our first celestial body that we're working on, and in any other celestial body, we need to keep humans as safe as possible. Take them away from the dangerous jobs, remove humans from harm's way. This happens to be a multi-billion-dollar market here on Earth, and a great need, and I'll explain a little bit about that as we go along. And so OffWorld is building this modular platform that allows us to expand from these terrestrial deployments that we're already undertaking to a series of space-based deployments that will allow us to take that learning that we've undertaken both on the hardware engineering platform, on the software operating system, and the intelligence and autonomy layers, and take that baseline foundation that we learn here on Earth through millions of robot hours of learning and operation, and extend that with a minimum delta cost to in-space and lunar and other celestial body environments. As you go further up the design stack of operations and architecture, the value proposition of the intelligence, the experience, and the insights and the data becomes ever more valuable. And OffWorld is building a platform for which the whole community can undertake and build third-party components and parts with compatible interfacing and integration so that we can undertake any number of tasks and systems and variety of solutions that we need. So if we need to, if a company needs to extract space debris and clean up debris, we can use this industrial Lego kit to put systems together to undertake that task. If you need to do processing in space or on the lunar surface, you can use the same platform, dismiss an extreme number of initial non-recurring engineering costs, use the platform and build your app on top of that so that you can build your function as you go forward. So OffWorld's operating architecture is enabling us to reduce the cost of terrestrial industrial operations at a CapEx and OpEx level by at least 10x, by removing people from danger and in situ challenges, by creating scalable solutions that can grow with any number of robots that you need, and by treating hardware almost as software in terms of the level of pixelation and the level of incremental updates. We can update small subsystems of modules. Modules themselves are entire robots as entire colonies are operating in real time. And this allows us to undertake a very much of a rolling evolution of both the hardware and software builds as we go forward. And the way we came about this architecture and this strategy was through many years previously, I had started a lunar ice mining venture from 2008 to 2015, which really attempted a single leap of setting up extraction facilities on the south pole of the moon, a lunar supply chain, and propellant depots in low Earth orbit. We treated that as the econometric equivalent of an offshore oil rig, with the challenges both economically, from a market perspective, and from technical challenges. And that ended up being an $18 billion proposed venture. And although I think a lot of the technical risks we eventually managed to get on par with possibly some of the worst propositions of terrestrial large-scale energy and mineral builds, the challenge was that the market risk was off the scale. If you build an oil rig, even if it costs $50 billion for an offshore oil complex, you know you've got a market. The challenge with the space resource sector, or practically any proposition beyond geo today, is that we may be aware of what the market can be, but we don't know yet who the customers precisely are en masse, who is going to provide the scaling capital, the scaling revenues. How do we reach down a supply chain to end users to ensure the validity of our assumptions in the business models? And a whole range of issues that lend a great deal of vulnerability to single-shot lunar and asteroid and other type ventures today. So how do you break that down? And what are the constraints? So we looked at really the proposition that we had and said, look, if we can't make it in space in a single shot, let's continue finding a way to build our skills up, to build the capabilities so that we can get there at some point in a step function. So we looked at what we had in terms of our design architectures and crystallized 4 key aspects out of this. This is basically the formula of how to build a space program today from scratch. In space, you ideally want no fixed infrastructure if you can help it. You don't want to have humans in place, astronauts in place, doing the basic industrial level labor. It's too expensive and it's too dangerous, and it doesn't scale. You definitely don't want to leave an environmental footprint, not just for benign purposes or ethics, but simply in space, in variable gravity. The last thing you want are clouds of regolith dust being kicked up, or worse still, perpetually in an exoatmosphere. And lastly, where you can help it, you want to avoid the use of consumables so that you don't have a front-loaded supply chain going up from a deep gravity well into shallow gravity wells. If you can reach those 4 ideals of strategic architectural design, then we believe we're onto something. So we took those constraints of architectural design requirements and identified a range of technologies, techniques, and capabilities that we would need to integrate. And naturally, we're not going to bring this whole puzzle together ourselves and do this. We're looking in many ways to where we slot into the architecture as we go forward into the space arena. But all of these capabilities and requirements are required when you're building a platform scale system. And we came up with a new robotic generation of architecture, systems that we believe should be small, extremely robust, highly adaptable, be based on electric power, so try to avoid consumables or propellants or hydrocarbons. Most importantly, to be autonomous and learning, using machine learning, deep reinforcement learning, and other techniques as they become available, and to be modular and reconfigurable to enable the production costs to be lower. And that allowed us to put that context of what we want to do into a master plan where we are going to go step by step into the solar system. Our first target is to solve industrial problems here on Earth, such as mining, construction, infrastructure repair, tunneling, and others. And that in itself is the foundational blueprint for what we need to do to build civilization out in the solar system. So having our machines characterize the levels of intelligence needed to build civilization here on Earth allows us to go forward and do that in space. And when you look at what's required from Earth, in space, on the moon, around the asteroids or Mars, there are some basic fundamentals. You've got to look at gravity, the presence of water, the challenges of dust, radiation, thermal cycles, amongst a number of others. And there are risks associated with each other. So being able to characterize those risks and concerns and putting them into a sequence of how do you build forward? What are the techniques and technologies and capabilities that we need to address here on Earth that can allow us to generate revenue that also then translate to space-based capability? So the first ones we're focusing on are the ability to undertake exploration and characterization, optical and other sensor characterization with our robots terrestrially, to undertake excavation and mining and processing of ore bodies, and to undertake construction and assembly and manufacturing. Those pieces allow us to create the baseline platform, as we can then have third-party customers and partners build on that platform to continue the quest to settlement and colony-level technologies and techniques. And we've been building this architecture today. We've been focusing on the main architecture, collaboration and intelligence systems. What are the power architectures? How do we undertake the software operating system and the machine learning? And then building a lot of other things as we go forward, step by step into ever more extreme environments. And so one of the big problems then, and one of the big questions is, then how do you pay for all this? Well, OffWorld is built only on commercial contracts. We don't have any investment nor debt. And so the company is growing cash flow positive year on year. And the first fundamental problem we've been addressing is how to solve this issue of mining. So currently mining is an archaic 19th century process going on with some technology toys to make it a little easier, but it is still tough, and it is no place for people to be in the 21st century. Today, the ore bodies that we have in 2020 are becoming extremely remote. The grade is becoming low. The available ore bodies are becoming deeper and deeper. So the last big open pit mines have probably all been discovered on land. The new ore bodies are going to be primarily deep underground ore bodies or potentially seabed level ore bodies. So our job is to take people out of these environments and replace them with our robots. Fully autonomous operation so that they will be curated rather than controlled, with increasing autonomy as we go forward. In terms of, do we know whether there are specifically ore bodies on the moon or Mars, concentrations of mineral rather than fragmented regolith? I don't believe we have definitive data yet. There hasn't been significant mineralogical mapping of concentrations of mineral to that extent. So a lot of the characterization has been done on base regolith compositions. So there's a lot of theory that the dynamics should be similar, but not yet. But what we do know on Earth is that we do have ore bodies. And a lot of these ore bodies are now deeper and deeper. And the current industrial processes for undertaking and extracting that ore is through the existing supply chains of the mining and industrial equipment market, which is now over $100 billion market. But the challenges are that we can't export this kind of technology out into space. The machines that are used in the mining sector are getting insanely huge. The power requirements are huge, the maintenance, the life cycle costs of a vehicle like this is around $50 million now. 5 million capex plus about a 45 million operations and maintenance burden. This is becoming untenable, especially as you consider, if you can see this, as you consider that the market in the mining industry, the demand for mineral is increasing significantly, and the demand is only going to get higher. The concentration or the grade of mineral is dropping of economically available mineral with conventional processes. That gap that is emerging between these 2 points is an increasing pressure on the mining industry. This is the first opportunity for the space sector. This is where the space mining industry needs to start. Earth is a celestial body. We need to learn the techniques of how to mine here on Earth. First, understand the differentiation between Earth environment and the space, lunar and other environments, characterize the delta, and then we only have to invest in the delta engineering costs, not start from scratch, not have one iteration every 3 years. We will have millions of robot hours of operating time before we launch our first operating colonies onto the lunar surface. That is a huge advantage, both from the machine learning side, from the hardware operations side, and the software system. And just yet another driver. Every year, we have increasing numbers of deaths of people. This is just very sobering from last year. People die in a moment, in a blink of an eye. When you don't think it, when you don't expect it, there is a great challenge just to normal operations. People are in extreme environments where they shouldn't have to be, and the slightest error or mistake or a split moment of bad luck can end someone's life. And by removing people from these situations systemically, not only can we increase productivity, not only can we refine the environmental impact, but we can save many hundreds of people's lives from these systems by taking people out of harm's way and just having these autonomous robots operating instead. So we will take the big idea of taking conventional mining and pixelating and fragmenting to swarm robotic mining architecture. This has been, from our first commercial contracts, the strategy that we've been taking. So instead of having a broken toe in the 15th or 16th century and losing your leg, we're going from slicing your entire leg off to now laparoscopic surgery and even non-invasive means of repairing today. And so we can use these robots to undertake precision mining, which is especially valuable for small ore bodies and narrow vein mining. There is a multi-billion-dollar market in this system. And this allows us at least a 15x cost advantage when compared to conventional mining and other industrial operations. So this is an example of the generation 1.1 robots, autonomous robots that we've been building. We've undertaken design and build of a number of different tools and end effectors that primarily our objective being, can we just touch rock and break the rock without force? So we focused a lot on applying high intensity energy of different formats to the rock. Can we characterize the fragmentation and how it breaks? And can we precondition it? So we've got a lot of good data in that. And we've undertaken testing on many different aspects of the hardware and the software. So OffWorld is building the full stack, hardware, software, operating system, intelligence layers on top. But we don't want to build everything, ultimately. The approach we're taking is to build a modular platform and architecture where we can swap out tracks for legs or wheels, or even impellers for undersea operations, or thrusters for in-space operations, for example. And learn how to characterize each mobility system so that it's a self-contained piece of unit that allows us to build and go forward. And as we put together the initial modules with the first tools and the first components and subsystems, we're characterizing not only the mechanical and system level integration and subsystem level capability, but also how do these systems operate in unstructured environments. We have a test mine that we operate in right now, testing some of the units. In fact, the Digger 1.1 that is on display in the exhibition hall has been out on several field tests already. And by characterizing this whole integration of hardware in structured and unstructured environments, creating characterizations and if you like, normalizing the behavior and understanding the behavior in different conditions, and then understanding material flow as well. How do you handle material autonomously? These are some of the hardest and most challenging problems that haven't really been addressed. So the field of robotics today is advancing rapidly, and a lot of the, let's say, commercially successful ventures that are out today involve flat, structured environments that are usually clean, where dust and other environmental hazards are controlled. We're expanding out now to sidewalk level environments, and those sidewalks for small payload deliveries involve observation to avoid people, to avoid traffic, to cross roads, and a lot of work being done in swarm, drone, and other autonomous flight capabilities. But the real next level opportunity is ruggedized autonomous robots collaborating in hardened extreme environments. This is as yet a nearly untouched field, but it's the field with the greatest degree of promise because the hazards are the greatest. The challenges to human life and limb in these environments are the most significant. And the variation of tooling, of actions are complex. So this is a big challenge to undertake. But the approach we've taken at OffWorld is to take the complexity of an entire architecture, for example, mining an ore body, and breaking that down into species of robot with one or two tooling tasks, and then breaking down those tooling tasks into ever finer control operational tasks, and applying then either coded or machine learnt operation and control to those tasks. And this is giving us a significant advantage that within a few years we'll be able to operate colonies and swarms of these robots of heterogeneous species, collaborating and communicating together, undertaking end-to-end programmatic tasks and architectures in ways that we haven't imagined possible before. And we built a number of robots in our Generation 1 systems. We've built payloads, and if you look at these, they do kind of look steampunk. We've got rugged, hardened, heavy-duty machinery and payloads that are operating under control intelligence. So it's a mixture of the most leading-edge, world-class machine learning intelligence and operating systems with the most innovative implementation of hardware integration, subsystem development and test, and then where possible, taking off-the-shelf tooling and integrating those off-the-shelf tools that have undertaken already millions of hours of test in normal and extreme environments, and integrating those within our systems. So where we can, we'll go off the shelf. Where we have to, as you see here, we develop specific payloads for those operations. And these kinds of architectures, as I said, rely on a high degree of autonomy, of intelligence, and control operating systems in the architectures. And the way we've approached building these colonies of machine intelligent robots is to take from first principles the challenges and the requirements of mobility, articulation, actuation, and tooling, sensing, characterization, and building all of those tasks and functions into a decision-making system that allows these robots to have increasing autonomy. They're not there yet. They can't operate for days alone. But every week, every month of continued development that we undertake, we are on an exponential curve of capability with these architectures. About a third of the work that we do at OffWorld is focusing on developing the underlying core technologies for machine learning, which will allow us to take any industrial task in the future, characterize that task by human learning and human teaching, and very rapidly have the systems autonomously take those architectures forward. And many of the team that have developed this machine learning architecture under the leadership of Ilya, our machine learning architect, OffWorld, have been developing a system that allows us to accelerate the fidelity of the machine learning capability in the real world, way beyond what we see in simulation. So as you can see, I mean, for example, here we have neural nets then characterizing where to undertake chiseling. We've undertaken simulations on mobility. How would you undertake learning? How do you apply neural nets and deep learning to really take the existing environments, continue taking inputs for positive growth, and continue that learning? As you can see, we can start increasing the learning quite rapidly when you put human demonstrations in the loop first. And tomorrow, Ilya will be actually debuting at our booth, 3:30, the OffWorld Gym, which is a new system we are developing to allow the community to access real-world environments that OffWorld is building and characterize and build their neural nets to optimize for specific goals. And this is going to be a community-led effort that Ilya will go into tomorrow at our booth. And you can see more about that at gym@offworld.ai. And bringing all that together allows us to undertake a significant data model. As we know from many ventures that are out there today, especially in the constellation field, the value of increasing data, both temporal and physical, from different sensor sources and different characterizations is significant. As OffWorld continues to deploy these robots for increasing numbers of customers across the world, we'll be able to take real-time surface-based samples of data from anything from soil, material, metal composition, atmospheric properties, what is the weather, what is the moisture, what are the UV levels, are there pollution levels, what are the contaminants, and we will build an ongoing and increasing data set to complement our orbital data sets, the likes of the world has never seen before. That will be an extremely high value proposition, offer a lot of opportunity for downstream providers to gain intelligence and support from that. So this allows us to build a new type of workforce of different species and capabilities. And for example, we can now undertake tunneling, autonomous tunneling, unlike large-scale boring and tunneling machines that often get stuck in variations of rock, whether they're hard rock or soft rock. Off-world tunneling architecture and robotic squads have a high degree of resilience. They're able to break the rock, move it, characterize and understand when you've got soft rock or soil, whether you've got hard rock, change the approaches taken, all autonomously without direct human intervention. Humans will always be digitally available in the loop to help with anomalies and any breakages in the system. But for ongoing operations, we are talking about an autonomous set of robots operating collaboratively like ants to undertake these different tasks. Same for road repair or bridge repair or assembly, any number of new forms of system to undertake different tasks and capabilities. And bringing this to a bit of a close, when you start characterizing all of these capabilities and all of these techniques, and we build an industrial system that is able to increasingly, throughout the coming decade, handle ever tougher and tougher jobs of increasing complexity collaboratively, we can start thinking about the big issues and the big picture. And currently, as we are all aware, the risks and issues that our civilization and our life is placing on us today is possibly at a critical level. And critical in terms of the fact that the impact is not affecting us today, but we may be sowing the seeds for non-reversible impact sometime in the future. And if we are wrong and everything is fine, that's wonderful. But just in case everything is not fine, we do need to address these kind of solutions today. By building an autonomous industrial workforce that can undertake mining with 1/10 of the environmental impact, that can undertake construction without all the effluents and waste, that can process ore bodies inside the mine itself, avoiding tailing dams, avoiding processing plants, and all the pollution coming with that. If we can undertake these sorts of solutions terrestrially, we're off to a good start. The next step, I believe, before the century is out, is to start an exodus of heavy industrial activity off the Earth where possible before the end of this century. And by doing that, we can start to build large-scale space-based solar power architectures, take manufacturing off the surface of the Earth, use lunar mineral resources and volatiles where feasible, get out to the asteroid belts, and start characterizing and understanding how to manufacture and assemble and operate in space. Building space-based solar power systems in space, for example. The case is not yet made of whether this is really practical or viable, but we do need to find out the answers to that. We need to do some tests over the coming decades to see if this is possible. Terrestrial solar and wind power are offered up as solutions to non-hydrocarbon-based energy for our civilization. But our current 17 terawatts of consumption is a big ask of renewables. In order to have base loading requirements to ensure constant power, that calls for an awful lot of batteries. And those batteries require an awful lot of minerals, which would increase the excavation and the mining requirement on Earth considerably. The drive for that is a potential solution of seabed mining, and most of the current seabed mining solutions are alluvial-based, basically dragging vacuum pumps and other scraping technologies off the surface of the seabed, causing great risks and havoc to the biota and the ocean climate. So over the years, either we're looking at nuclear, fusion as the possibility may emerge, and space-based solar. And if we're going to build space-based solar power systems, we need to be able to scale. We need to be able to have autonomous systems operating seamlessly with millions of hours of experience already gained. There are many organizations working on advanced thin film and sandwich-based solar power systems, both for capture of sunlight and then transmission of RF downstream. And we can integrate these into large-scale arrays, which are readily built using struts built from lunar or in-space resources, and allow those architectures to go beyond demos. And I think a demo like this is possible before mid-century, so that we can start to figure out what are the questions and how do we answer them regarding space-based solar power. There are a lot of theories, we have a lot of architectures on how to do it, but the real advantages are that we can now use autonomous systems to build the hundreds to thousands of rectennas that we might want to do on Earth as we improve those and expand that operating architecture with the same kind of technologies, with the same operating systems, adding new capabilities and layers of control and avionics and characterization to different kinds of systems in space. And the real advantage of this kind of power is that you are generating all of that power off the surface of the Earth. The thermodynamic waste heat is not being generated on Earth. And you can have enough of an overage of power even to ensure that you can control the thermal variance that comes from all of that power being delivered to Earth and all of that heat being delivered to Earth as well. And as I said, OffWorld is building this infrastructure toolkit, solar system toolkit of a wide range of autonomous robots, configurable, growing constantly through commercial contracts. There are customer groups and market sectors and industrial sectors that have a real need for a new generation of autonomous systems, collaborating and working together in ways that we haven't seen before. So with that, I'm looking forward to seeing us all get to the lunar surface rapidly in the next few years. I think it's within our grasp. The political momentum is there. We need to match it with capabilities. We need to really drive forward and do this on a commercial basis. And it's OffWorld's plan to take the generation of 1.1 robots that we're building for our commercial clients and put those robots up into space in the coming decade to the lunar surface, start extracting water, minerals, and manufacturing basic components before 2030. And if you're interested, we're actually showing our Digger 1.1 generation Diggerbot in the exhibition hall this week. It's the debut of OffWorld systems in public. The first time we're showing this. So do feel free to come to the booth and check us out. And as I said, Ilya will be giving a talk on the machine learning aspects of this new advanced workforce tomorrow at 3:30. So with that, thank you very much. Happy to answer any questions. Thank you.
So this was a really nice presentation. I have no idea where everyone is. I guess people are just going to big name presentations, which is bullshit. What I was wondering, it's more a question on your vision. So if we go to another planet, we have like a unique chance to start a civilization again. And on Earth, we have this problem that we continuously want to mine more and more and more. And at some point, you have nothing left. So if we go to another planet and we have these robots, what's going to stop us from emptying just another planet and going on like that? So
I think for the last 10 to 15,000 years of our growing civilization and culture, our accountability supply chain has stopped at Earth. We don't account for the resources that we use on Earth in any way. We don't account for environmental impact, or we haven't up until very recently. In space, because we don't have atmospheres, we can't take anything for granted. The accounting and the accountability of every iota of the supply chain of what we do is going to be integrated into how we think and how we operate. So in that sense, it will be almost impossible and imprudent for us to go forward into space with a view to irresponsible exploitation to the nth degree. So we will be going into space, and people like you, people like us here, who are sensitive and aware of the system level issues in these new environments, will go to harvest and exploit what we can from those environments, not to the extent that is economically viable, but to the extent that is environmentally sensitive. Because to not do so, it's not just about morals or ethics. To not do so creates 10 to 100 times worse environmental impact than we have on Earth. On Earth, we have an atmosphere with currents, winds, that allow us to, in some ways, create the illusion of an ever-capable environment, an ecosystem that can absorb whatever we throw at it. But in space, what you mine and throw up in regolith dust in a low-gravity environment will hang and suspend. Electrostatic lunar regolith will surround your machinery and your systems rapidly. So we will be taking much more care as we go forward. And I think we have an opportunity as we step out of our environment of scarcity to create a new standard and a new ideal of how we go out into space, how we operate together collaboratively and collectively with a sense of inclusiveness and cooperation, and set a new ideal and standard that we will aspire to as we go out into the solar system and into the stars. That's what we have to do. We can't just take scarcity-based mentality with us.
I'd like to thank you for your presentation, and I have a question for you about the robots going into space. So you have robots that are currently operating on Earth right now. Are there any major challenges you see moving forward in deploying these robots into space? Like, are there any technological advancements you need to make, or are they ready to go right now?
No, there are one or two challenges to overcome, yes. I think on the hardware side, some of the critical issues include tribology. So if we're using any form of fluids or lubrication, what are the issues there? The others are thermal variance. How do we operate in cryogenic environments, both from a mechanical resilience perspective and electronics perspective? How do we manage thermal dissipation? In the coldness of space, these things will get hot. How do we figure that? How do we manage power delivery? Electronic rad hardening, of course, is an issue. So there are a number of technological hardware challenges that will have to be upgraded. So we'll create special standard extensions for some of the space-based modules and also some of the undersea seabed modules as well. There'll be some variants on that. But I think one of the real powers of this type of architecture is that the operating system can remain common. A lot of the operating layers remain common, and even the control actuation and systems remain common. The variance in delta becomes something ideally suited to intelligence, machine intelligence, that can then characterize the variance of, say, a gravity environment, and within a few hours or days, create a new set of input variables that allow the common control platform to then be sensitive to a different environment. So that's where the learning opportunities really start to have a significant advantage, is that you can throw the common systems into uncommon environments and have them adapt rapidly.
Thank you.
Jim, thanks a lot for this excellent presentation. It was very comprehensive. I liked it very much. As a venture capital investor, I'm always impressed by founders who can make it without an external investment, so chapeau. Having said that, I also know that the mining industry on Earth is very conservative. At the same time, it's an under-digitized industry. Can you elaborate a little bit on your market entry? What's the status on that?
So actually our first client was a mining company, one of the big miners. And the challenges the mining industry is having are common to all of them. They are facing an existential crisis. Over the next perhaps 10 to 20 years, the ability for conventional mining architectures to continue maintaining profitability comes under increasing pressure. And the mining industry is out of time to look for new solutions. So putting people in mines which are getting ever deeper and deeper, which are getting ever hotter and hotter, is impossible. We can't continue that way. So you're absolutely right. The mining industry is extremely conservative. They've done things for the same way for 150 years. They know how it's done. But there are pockets of innovative desperation and looking to solution providers to find a way out. And it just so happens we were there at the right time with the right proposition, and we're able to build on that. And we've learned now that the challenges and the nature of the challenges, human safety, the cost of labor, the availability of the right type of labor, the challenges of project costing and bidding, the mobility of labor, all of these issues causing challenges in the mining sector, construction, infrastructure. And this is when governments of the world today are planning for another 2 billion people or so in terms of infrastructure build by 2050. And those 20 to 30 year timescale projects are starting now. And there is not enough workforce capacity of the right type of labor to do that. Otherwise, you face immigration problems because no one here in Washington, D.C. wants to roll up their sleeves and start building roads. So again, you have demographic challenges in that the Western world demographics are going to far more technological-based skill sets and labor, and the ability to operate and machine these tools or man these tools are being called on by labor from different parts of the world. But the challenge is, as we all are aware of, the pressures of moving demographics. You know, today and in the coming years and decades, there is an impasse occurring, and the solution is let's take people out of harm's way. Let's create a new form of workforce and build these systems that enable us to basically develop our space program. So luckily, we have the mining and commercial construction sectors paying to develop OffWorld's space program. Okay, if there are no more questions, one more here, and then I think we'll almost be out of time.
There's an opportunity to set the standards for interoperable planetary robotics open now. In the near term, what sort of architectural layers are you going to be able to expose that will enable third-party players to model and work with?
So next year, probably by third or fourth quarter next year, we'll open up the standards for interfacing, operational architecture, an API plugin for modules into this system toolkit, so that manufacturers of existing hardware, like power tools and other things, or teams that want to build specific pieces, will have standard interfaces, both on the software and hardware side, to connect in. So then we can create an open marketplace together and start leveraging the opportunities to go out. So you don't have to build, we're not going to build thrusters and propulsion systems. So third parties can just build the interface pieces to use their existing hardware onto our rockets, onto our robots. And actually at our booth, you can see some models of some of the flight systems, the space-based flight systems that exist as well, or will exist. Okay, so with that, I'd like to thank you very much for your kind attention, and please do visit the booth. Boeing is next to our booth, but you know, don't worry about them being overshadowed by OffWorld. Do enjoy it, and enjoy the rest of the conference. Thank you.